Mira, Dontcheva, Aaron Hertzmann, and Adam Wilson. It's during my internship at Adobe Research. So my talk is entitled with MatrixWave visual comparison of event sequence data. So our world is full of events, and we encounter them in a particular order. For example, to attend Kai.
You come closer to the mic?
Yeah. Yes. Okay. Sorry about that. So, for example, to attend Kai, I need to register online and then purchase my ticket and flew here. So we call that as an event sequence. And in fact, in addition to personal life activities, event sequence data is ubiquitous in many application domains, such as web server logs and usability study logs. Let's take web server logs as an example. So from those data, we can learn how users navigate a website. For example, here, one user may land on the home page and then browse a different program, workshops at Kai. And another user might land on the home page and directly go to the housing information. And the third user might go to the registration page after a Google search. And here I'm only showing 3 users. There might be thousands of users visiting the Kai website. So every business is interested in studying user behavior from those log data. And it is important to know those kind of questions. And here I only list several basic questions, such as how many users visit a particular page at a particular step, how soon do users leave the website, and what paths do those users mainly follow. So one of the popular visual analysis methods for this kind of log data is the Sankey Diagram. So the Sankey Diagram aligns all the event sequences based on steps, and then further aggregate them based on page visits. For example, here, the user volume visiting a particular page at a particular step is shown as a rectangle, and the user traverse between 2 pages is shown as a link. However, one downside of this visualization is the edge crossing problem. Here, I only show 20 pages, and there are hundreds of pages at Kai website, and it's going to be worse than this. In addition, there's one important task that have been overlooked in the past is the comparison of event sequence data. For example, you have 2 web logs extracted from different time ranges, and as a web analyst, they want to see the major differences between them. So this kind of visual comparison tasks is critical in many scenarios. For example, when we do A/B testing, we want to compare the user behaviors to see which design is more effective. And you also want to compare user behaviors from different geolocations so you can make appropriate strategies for different populations. So we have 2 problems to address today here. The first one is how to visually encode large and dense event sequence data effectively. The other one is how to support visual comparison of 2 event sequence data in visualization. Let's look at the first one. So let's suppose we just have one simple event sequence data, and its corresponding Sankey diagram is shown on the right. We notice that even for this simple data set, there are still many edge crossings. And to avoid this edge crossings, the literature suggests matrix-based representations. So we can transform those no-link diagram into a matrix. Let's just look at the first 2 steps. So to transform these first 2 steps into a matrix, we use the first step as rows, second step as columns, and transform those links into squares. And in this matrix, the size of nodes represent the volume user visited that page at that step. For example, here only 1 user visits page B at step 1, and 3 users visit step 2, web page B at step 2. Similarly, the thickness of the link and the size of the link represent how many users traverse between 2 pages. For example, here only 1 user stays in page B between those 2 steps, and there are 2 users traverse from A to B. And notice that the link is represented as a square in the matrix. That's why it can eliminate all the edge crossings. So if we do all the kind of transition for every consecutive steps, we have a series matrix. And I want to point out another very special links in those two visualization is this drop-off links that is important in web log analysis. It represents how many users leave a website. For example, here, one user leave the website after step 2. So we have this kind of matrix-based representation. Although there's no edge crossings, there are still limitations. The first one is it duplicates all the nodes when it's taking more space to draw those nodes and matrices. The second one is it's very hard to trace the path in the event sequence data because it breaks the continuity. So we propose to rotate and concatenate those matrices together so you don't need to draw all the duplicated nodes. And also a path can be traced in a zigzag manner. So we have this visualization we call MatrixWave. Compared to the Sankey diagram showing about the same amount of data is much cleaner. And it also scales for this kind of data, which is 5 times denser and larger. So let's move on to the second problem, is how to support visual comparison with 2 event sequence data in MatrixWave. So there are mainly 3 types of methods for visual comparison. The first one is juxtaposition, which is side-by-side comparison, and superposition, which is using the overlay of 2 visualizations, and explicit encoding, which to compute the difference and show as the visualizations. In our study, we choose the second, third approach because a juxtaposition of 2 MatrixWave visualization will place the corresponding elements far apart. And I need to, something like this. And I need to remind you that for each link or node, we have 2 values and potential a change that we compute. So this is our final MatrixWave visualization design. And we use superposition to embed 2 data together in a single MatrixWave visualization, and use explicit encoding to show the data changes in color. To further explain, we take the average of those 2 values and use the same size encoding as I introduced before. And for changes, we directly use color-coded nodes and use the background color of the links. Here, purple means decreasing, orange means increasing. And next, I'm going to show you a demo of our prototype. Let me switch to the browser. Okay, so here, 2 event sequence data have been loaded into this MatrixWave visualization, and I'm only showing the first 2 steps. And one data is the server logs before a major website redesign. The other is after. So suppose that you're a web analyst and you want to compare user behavior changes, and you want to see whether those changes is due to this website redesign. And you want to know where the user drops and how soon they leave the website, and you also want to know what are the main traffic paths. So let's take a look and zoom in a little bit. So you can reorder those nodes based on volume. So you can see that the website within most as first step is the home page, or by change, so you can see the increasing, decreasing more clearly. So for this home page, it has many links to the second step, and most of the links are purple, meaning the traffic is down. And when you hover over on those links, you notice that the traffic is 100% down, meaning that there's no user follow the same link in the second data. So those links might not exist anymore in the second design. And if you observe the black squares on each matrix cell, which represent the traffic volume, you'll notice that most of the users stay in the home page and go to the product page, which has 250% increase. And this help page has 390% increase, which is huge. So let's take a look at it. By clicking it, you filter out other unrelated visual elements. To examine what happened next, let's review all the other matrices and look at the second step. So after this help page, It seems that the user went to 4 different pages, and one with very great increasing in traffic is this TV page, because you see very bright orange here. So it makes sense because the TV page is where you host most of the help tutorials. So let's click that to explore further. And after this TV page, which goes to step 3, if you observe all the size of the black squares, you notice that actually most of the users leave the website because you see a very large black square on in the drop-off column. So they leave the website after viewing this TV page. And if you follow those blue lines, which showing the path of the users, it either ends at step 4 or ends at step 5. So it means that the users leave the TV page a few steps after. So maybe they found what they need, maybe they don't. So further investigation is needed. And if you hover over on those drop-off nodes showing how users leave the website, here is like 60% increase, 100% increase, and 170% increase. So the user leaving the website faster and faster. So those questions are insights were valuable for the web analysis. So they need to examine the data. So it's just a short, brief demo. Let me go back to slides. So before we come to this, the final MatrixWave design, we tried different design alternatives. For example, for nodes, those 2 approaches we use is to use 2 bars to represent those 2 values from those 2 data sets and place them side by side. However, it's now very easy to do the comparison by explicitly encoding it in color. Similarly, we try different design alternatives for links. For the 2 approaches above, we break each matrix cell into 2 squares or 2 triangles and use color density to encode those 2 values. Again, it's not very salient for data comparison. So we try to use color to encode this change. So we color-coded the link square as the approach is shown at bottom and first one. However, when the links become too small, you can hardly see the change. And so we tried another approach to use color density to encode the traffic volume and use another color scheme, purple-orange, to encode the traffic change. But the user might get confused about those 2 color schemes. So finally, we took a kind of like a hybrid approach, which I introduced before. So to evaluate the effectiveness of this MatrixWave visualization, we conduct a user study by comparing it with the traditional Sankey diagram. But the traditional Sankey diagram does not support data comparison, so we developed a extended version of this Sankey, followed by same visual encodings and interactions in MatrixWave to guarantee a fair comparison. So in the user study, we have 12 participants and design 8 comparison tasks, including the comparison of 4 important elements in event sequence data, including node, link, step, and path. And we use realist data to conduct the study. And for the results, here is the accuracy and completion time for the nodes comparison tasks. You can see that the 2 visualizations perform similar. That makes sense because they are using similar visual representations. And for link comparison tasks, we can see that MatrixWave was more accurate. So which match our hypothesis because there's no overlapping, no edge crossings in MatrixWave. And for step comparison tasks, MatrixWave was either more accurate or faster because those tasks involve the access of a large number of links and nodes between 2 consecutive steps. And finally, for path comparison tasks, MatrixWave was also more accurate. So OR in general, MatrixWave had a better performance than Sankey. And from the user preference, 8 up to 12 participants prefer MatrixWave design. And we also report the user feedback in the paper. And for time reason, I won't discuss it in detail here. you can refer that in the paper. So, as for future work, we'd like to further evaluate this MatrixWave visualization with domain experts with a more realistic work settings. And we also want to extend this visualization to support the comparison more than 2 data sets. Thirdly, because recently we don't encode the temporal information of each event, so that is the time step of the event, and we are looking into add those kind of information into the visual encodings. And in the end, I want to thank all my co-authors and thank all the expert users we worked during this project, and thank all the participants who in the study, and also thank for your attention and take any questions. Thank you.
So if you have questions, you have a mic right here in the middle. Please give your name and your affiliation.
Thank you. Sorry, I can't hear. Oh, yeah, yeah. Okay, so we said that work in our paper, and the Jian code is showing trees, and is the paths of each, because it's showing trees and it has the levels, the paths for showing those structures is twice longer than the paths in MatrixWave, because it's used, I think it's used columns for for nodes, and use rows for nodes and columns for the parent-child relationship. So if you trace a path from the root node to the leaf, in MatrixWave it takes half of the distance. So our visualization is more compact, and also we are talking at different domains and problem. That's a good question.
I see. Thank you.
Thanks.
Thank you very much for a nice talk. Jae Chu from Korean University. So I was wondering if this technique can be also applicable to general multivariate data visualizations. So for example, this Sankey diagram is also very similar to parallel sets.
Mm-hmm.
So so those multivariate data without necessarily the temporal information could be also applicable for this, I think. So in that case, I guess reordering between those different dimensions might be also important. So in your case, also you could switch between those matrices from your sequence. So I was wondering if you can comment any about those aspects by using your technique.
That's a great suggestion and great question. So I think it's applicable for multidimensional data. If you view each matrix row and column as an axis in similar to parallel coordinates, and if you place the nodes in a very smart order, you will see clusters in the matrix, and that's a strong signal that you want to see when you analyzing multidimensional data, so you can see where the most correlated variables are and across all the dimensions. And yeah, so I think that's a great suggestion. Maybe it's a good future work to pursue.
Okay, thank you very much.
Thanks.
Okay, no more question. I have one question. This is a very astute visualization, and I'm just wondering, is there a way to get some requirements regarding the evolution on the hierarchy of the web page? For instance, thanks to an kind of automatic analysis of this matrix, you can give requirements what you should modify, or
You mean requirements as a user requirements or
no, and the developer?
Developer requirements? Yeah, actually, I don't know how to answer that question. But it's currently we aggregate all the nodes as web pages. So actually, it shows different sections of on the entire website. So if you see a cluster, you can see where the most changes are happening in different sections of the website. I think that might be one. If you give requirement to the developer, you want them to have a good good hierarchy that reflect different user behaviors. If the order nodes is placed randomly, the matrix might not be effective.
Okay, no more questions. So let's thank again the speaker and congratulate the authors.